Okay, so what is a polynomial? Polynomials are like this. Poly means many, right? So they have a lot of terms. But even one that's only got one term is still considered a polynomial. It's all about the powers on these things. And what makes it a polynomial is that it has like a power, like power of 3, power of 4 is fine, power of 2 is fine, power of 3/4, nope, you can't have fraction powers. They have to be normal powers. So that one, not a polynomial. And you might think this isn't a polynomial either because it's only got one term, but it's even okay to have one term. What you can't have, though, is just a constant like y equals 5. That is not a polynomial. It's called a constant. A polynomial has to have at least an x in it. So it needs x to the 1 or x to the 2. Again, it can't have fraction exponents, and it can't have negative exponents. So basically, if the numbers are normal, then it's a polynomial. If the powers are normal, then it's a polynomial. All right. The degree of the polynomial is just the biggest one. The most common mistake we get on this is people think that the degree of this would be degree 3 because they'd take 2 for that one and 1 for this one and add them together and say degree 3. No, you just pick the biggest one. So what degree is this red equation here? Degree 2. And each of these things are called terms. It's got 3 terms. How can you tell a term apart from another term? Because it's got a plus or a minus in between. So there's this chunk, and that chunk. There's 3 terms. Okay, if they're added and subtracted, then each of those little things is separate, and they are terms. Okay, so what's the degree of this polynomial? It's got 4 terms, and it's degree 6. Does that make sense to you? Why 6? Because the biggest one's a 6. You do not add them together. This one's going to fuel a few people. What do you think the answer is? Degree what? Degree 4. Because it's not always the front one. It's just the biggest one. That one's the biggest one, so it's degree 4. Okay. This one will fool some people. What degree do you think that one is?
Degree 1.
I've heard 1 and 3, and both of them are wrong. What's different about this one compared to these? It's all factored out. It needs to be foiled. What degree would it be if it was foiled out all the way?
Degree 5.
I've heard 2. I've heard 5. Somebody just say the right answer, please. It's not 6. It's not 1. It's not 5. It's not 2. Come on. If I were to multiply this thing all the way out, do you get how it would have an x to the 3rd in it? But do you get how it will also have an x over here? And eventually those would get multiplied together, wouldn't they? The biggest one would be x to the 4th. If I multiplied this all the way out, I'd have an x to the 3rd on this side, and an x on this side, and an x times an x to the 3rd would make it x to the 4th. So that one is degree 4. And I know why people get confused on these other ones and start thinking that you add the powers together, because on this kind, you do add the powers together, because 3 plus this 1 on this 1 is for this parenthesis here. That tells you what degree it is on that kind. But I like to think of it as if you multiplied it all the way out. Let me give you one that's simpler. X plus 4 and x plus 3. How come that's degree 2, even though there's no 2's anywhere?
Because of the 1.
Yeah. And if I multiplied this out, do you get I would have an x squared? So you got to think of it as, if I multiplied it out, what would the biggest power be? So this one's degree 2. Think of it as, if you multiplied it out, what would it have? Okay, this one is multiplied out already, so don't add the degrees together. What's the degree? Degree 4. All right. Yes?
What if there's exponent inside of the parentheses?
So if I had x squared and then it was like this, that's a good point. That's another reason to not think like adding or whatever. Think about, if I multiplied this all the way out, what's the biggest degree that this would have then? Degree 10. Good. So if you multiply it all the way out, what's the biggest power it would have? That's what degree is. Okay, so let's move on to, if I look at a picture, I can tell what degree it is, or at least close, because I'm trained. I know from looking at it what kind of, is this a degree 3, degree 5? All right, and I'm going to teach you how to do that now. So I can look at this and go, I know what degree that is. That one's degree 5. This one right here. And I can tell you why. And it has to do with its roots. Do you get that that's a bounce? Like it bounced off of there? That's like a parabola has, right? And what degrees are parabolas? 2. So it's 2 because of this. And then this one's got a snake, which is kind of like one of these. Do you remember what degree this thing was? X to the third. Do you remember that X to the third graph? This snake kind of thing tells me it's degree 3. That tells me it's degree 2. To put it all together, it's a degree 5. Now, I'm not going to get into complicated stuff like imaginary roots yet, but this is degree 5 because I can see 5 roots. 3 for that, 2 for that. Now, I don't expect you to be an expert as much as I am at all, but at least things like this, like parabola is a degree 2, right? So it's got at least degree 2 plus more. Yes? Correct. This does not count as it's all about the roots. Those root things are really important. This is a root, that's a root, and that's a root. You remember I was talking about the roots, the x-intercepts? They're huge. They're what you count. Okay. Now, for this next thing, it's about end value. All it's saying is, on this end, do you get it's going up? And on the other end, do you get it's going down? That's all you have to understand for end values is up and down. On the left side of this graph, that's this side right here, do you get it's down? And on the right side of this graph, it's down. Okay, so your end values are either up or down, and every graph has ends that either go up or down, unless it is this line right there, which isn't going up or down. That's the only exception, okay? Every graph is either going up or down on each end. So what would you say about this one? On the left, it's up, and on the right, it's up. It's that simple. How about on this graph? On the left, it's what? Down. On the right, that's it. Now, the cool thing is I can predict if you give me a crazy looking equation like x to the fifth, 7x to the fifth minus 4x to the third minus 2x plus 7, I can tell you what that graph's going to kind of look like. Even though that is a really complicated looking equation, I can tell you the end, how it ends. It's like how the story ends, okay? That one, for instance, now, I picked that one, but I'm going to have you pick it in a second here. But that one, for instance, if I made a picture of it, I know it's degree 5. And I also know I'm going to not tell you this other part of the thing that I know, but I'll tell you in a moment. I would say that this one, let me think now, would generally look like that. And it's down on the left and it's up on the right. Now, see if anybody gets to start predicting, being able to predict like I can, which way the graphs go, okay? So somebody give me another crazy graph that's got lots of like complication to it or equation, and I'll tell you what the graph would have to look like, and then I'll teach you how to do it. First question. Both of you. We'll start with you.
All right, so I'd say like negative x squared minus.
Pick up the difficulty level. Make it complicated.
Okay, 5 7.
You want x to the 7th or just 5 to the 7th?
5x to the 7th.
Okay. Come on, make it hard. Here's an easy one.
The square root of 2 to the.
Ooh, wait a minute.
Oh!
You broke it. And actually, I actually kind of like that because you said square root. That actually means a fraction power. We can't do fraction powers or it won't be a polynomial. So no square rooting.
So it's too hard for you?
Oh, ouch. It's just not a polynomial. Fine. I'm just going to end yours with a 7. Okay. So now if I had to tell you on what yours would look like, I would say I know that. Let me think now. Yours is up on this end and it's down on that end. Now what it does in between, I'm not absolutely positive, but I know that it's going to have, since it's got a degree 7, it's probably got 6 turns in it. So watch the turns. 1 turn, 2 turns, 3 turns, 4 turns, 5 turns. Let me make sure I did that right. 1, 2, 3, 4. Well, that's only 4 turns. My bad. Got to turn again a couple more times. 5 turns, 6 turns. There we go. It would look something like this. Notice how many turns it had. 1, 2, 3, 4, 5, 6 turns in it because it's degree 7. Because if I had, for instance, y equals x squared, you tell me how many turns does that have? Does it have 2? No, it always has 1 less than whatever its degree is. Okay, so that's got 1 turn in it, right? You know that one. It's a parabola. Looks like that, 1 turn. So what if it has, somebody give me another one. You think you got it? Cool. Well, let's just do one more and you predict it and I'll tell you if you're right or not. Give me a hard one. You can do that. Okay. Make it one, just finish right here because I don't have any more room. What? All right. I know what that looks like. Okay. I know but we'll see if she knows. What do you think? What would you predict this one is? False. Good try. All right. I know this one for sure is going to be either both down or both up. And I am for sure that it's both down. Down on this side, and it has to be down on that side. Anybody have a way of predicting yet? What do you think? If the degree is even, see, I picked 8 because that's the bigger of the 2 powers. If the degree is even, then they're the same. You've got it, except you got to know one more thing. If it's even, they're the same. As in they're both up or they're both down. How did you figure that out? Something you learned before or you just figured out? All right, cool. And then let's think about the other option then. What if it's not even? What if it's odd? Like degree 7. What if it was degree 7? Then what? Then they're not the same. Like one's up, one's down. Okay, but do you know which one's which? See, like this one, you know they're the same. I knew that they were down. Do you know that they're down? How do you know that they're down? All right. Now, they're not actually down. I fooled you. They're both actually up. So, how do I know that? Well, you can graph it if you want to be absolutely positive. I'm not just lying to you, but I'll tell you. All right, yeah, it's complicated to put in the calculator, wouldn't it? So, here's the thing. As soon as I identify the one that makes the degree, then nothing else matters. Only this really matters. That doesn't matter at all. And then to decide whether they're both up or they're both down, or whether one's up and one's down, the way you can tell is you look and see if the lead coefficient is positive or negative in front. Do you get that this one's a positive? Since it's positive, then it has a happy ending. So it's up on the right. If it's up on the right, and I know that they're both the same, then it must be both of them up. I'll give you another one like that. Y equals negative 16x to the 23rd plus 4x to the 400th. All it really matters is the one that's got the bigger degree, and therefore this one doesn't matter. And therefore it's positive, it has a happy ending, it's up on the right. Now how about, okay, and how about if you say on the left-hand side, do I know if it's up or down? I do. Do you? Because it's even, what are they? They have to be the same, so it must be up, up. Good. All right, I'll give you one more. Y equals negative x squared minus x minus 3. Okay, negatives running all over the place, including at the beginning. So what do I know? Is it has a happy ending or a sad ending? Sad ending, going down. And then how do I know if they're both going down or both going up? I know this one's down. It's even, so they're both going down. Very good. It's got to be one turn because this is degree 2. It's got to be one turn, so it's something like that. Except I can also tell you one more thing that a lot of people haven't been thinking about. The y-intercept on this is -3. You know that, right? So then it must be down lower. They must both be going down, and it must have a y-intercept of -3, so it must be down there. All right, so there's 3 things you know. You know the right side by looking at the lead coefficient. If it's negative, it's a sad ending, it's going down on the right. Next, you look at this and you see if it's even, they're both going the same way. If it's odd, they're going opposite ways. And then you look at the y-intercept, and if the y-intercept's negative, you must be going through down here, below 0. All right, so if you understood what I just showed y'all, I'm going to give you a problem to, like, you make me a sketch that could be right then. Yes? Mm-hmm. Nope. It's the bigger one wins. So if this has got an x to the 3rd, and an x to the 5th, and an x to the, and an 8x to the 9th, I just look for the biggest one, and the biggest one wins, and these don't matter. And now I say lead coefficient's negative. It's -8, so it's negative, so it's a sad ending. And are they both the same, or are they both different? They're different because this is odd, and odd things are different, right? If you see a guy walking down the hallway in his hands, you might be like, that's odd. He's different, right? Okay, odd is different. Okay, so it's odd, so they're different. So this one must be up, the other one must be down. And then how about this? How many turns can this thing have at most? 8 turns. So here's some turns. 1 turn, 2 turns, 3 turns, 4 turns, 5 turns, 6 turns, 7 turns, 8 turns. See, if I'd have had one more turn, it would have been going up. But it works. Yes, yes. All right. Yes? All right. That gets more complicated. What if I could factor it and it was like this? Then, and this one was squared, then here's the hyper advanced way to do it. If you can factor it, then you can know that it touches at 3 and -4 and -4. And then you could know it's a squared, which is like a parabola, so it's bouncing there. Then you could multiply this all out in your head and say, okay, well, it's going to have an x to the 3rd in it, right? If I multiplied it all the way out. So it's odd, so that means the ends must be different. Is the beginning of the story a negative in the front? Positive or negative? Positive in this case. It's positive lead coefficient. If I multiplied it all the way out, the front term would be positive. So therefore, it has a happy ending, so it goes up on this side. It's bouncing at this -4 right here, so it must be going down like this and bouncing here and going opposite directions. How come they're going opposite directions? Because it's degree 3. A lot to digest all at once, but do you get that it said this was degree 3? That's one question. Do you get why it was degree 3? Because if I multiplied it out, it'd have an x to the 3rd in it. Do you get that degree 3 means they must be odd and therefore opposites, opposite the normal, okay? And if it had come out as an even degree, they'd both be going the same way. Next, do you get that since they were factored, the factors give you the roots, the zeros, the x-intercepts? And so I knew that this was going to touch at -4 and at 3, and that's why I put a dot here and here. And do you get that this one was a bounce because it hit at the 4? It has a squared, so it was a bounce right there. All right, there's a lot to know, but you don't have to know everything today. Let's just get through a few more slides. You can ask more questions if you want. All right, so on this one, do you get it's degree 2, and therefore they're even, and therefore they're both going the same direction? Why are they both going up and not both going down? Because it's positive, and if it starts with a positive, it has a happy ending. Okay, goes up on the right, and if it's going up on the right, it has to be going up on the left because they both have to be the same. How about this one? Why is it going down on the right? Because it has a negative. And why are they both going down? Because it's even. Even. It is easy to confuse even and positive in your head. All right, how about this guy? It starts, I always like to think of the right side first, because you know what? The degree doesn't even matter. If it starts with a positive, then it has to be going up on the right. Has a happy ending.
Always on the right.
Always on the right. Only the right side and this thing go together. If it leads with a positive, then it must be going up. Okay, but then this degree 3 tells me that they must be doing opposites. That's why it's going down over there. Okay? Without even looking at this graph for a second, do you get it have a sad ending? Do you get they'd have to be going opposite directions? So now that I reveal it, not that you can't see through it, but do you get that it does have a happy, or a, sorry, sad ending because of the negative in front, and they're going opposite directions? All right. Then, do you get that this is one of those fancy snake kind of ones that's degree 3? And that's why it's got a degree 3. The root, you can tell by looking where it hits the x-axis is where what it's all about. And where it hits that, if it's special, like this special kind of snake curve like this, then it's a degree 3. If it's bouncing like this guy, then it's degree 2. Or, unfortunately, you're in higher algebra now, so you have to be able to handle complications. If it's even, as long as it's even, that could be degree 2 or 4 or 6. Up until now, you only knew, everybody knew this as, oh, that's a parabola, it's x squared. But actually, when you graph it, that could be x to the 4th or x to the 6th. Why couldn't it be x to the, like, 7th? Is it's even, and they have to stay going up together, right?
What about x to the 10th?
That's even again, so it would be fine. That could be x to the 10th.
So it could be anything even.
Yep. And this could be anything odd, like degree 5, degree 7, degree 9. This is an odd kind of curve, and so that means it could be degree 3, degree 5, degree 7. All right. Do you get, though, that it's got a positive in front, and therefore it has to have a happy ending? It must be going up on the right side?
Yeah.
All right. And since it's odd, they must be going opposites, so it must be down on the left and up on the right? Yes? You don't have to multiply this all the way out. If you did, then yes. But you don't have to actually multiply this out. You just have to, in your head, imagine for a moment that you multiplied it all out. And you'll know, oh, well, I'll get an x squared then, at least. You'd know that. And then I'll have to multiply that by an x. That's how I know it's x to the 3rd. You don't have to actually multiply it all the way out. Yes?
What if there was a negative before the parentheses with x minus 3? So that would be negative. But x is negative also.
Okay, well, you're getting really complicated here. But if I multiplied this one all the way out, do you get the lead term would be negative?
Yeah,
But if I threw a negative in here, do you get it would be positive now?
positive.
So you got to act like if I multiplied it all the way out, the lead term would be positive. So it has a happy ending up on the right. And since this is going to be degree 2, am I lying?
No. Yeah, you are.
Yeah, it's actually degree what?
3.
3. So therefore it must be what on the left?
Degree.
If it's degree 3,
X.
what's it doing, down or up on the left?
Up.
If it's degree 3, is it supposed to be the same or different? Different, and therefore down on the left. That one's going down on the left. All right. So we're getting more complicated than we have to be, but I think it's good for you to see all of those things. All right, next thing is increasing and decreasing. This is the easy part. I bet you if I show you this graph, you can tell when I'm increasing and when I'm not. Do you get that we in the United States read from left to right? Therefore, we interpret this as you read from left to right as increasing. Do you get how this little part that's in blue is all increasing until then? Because as we read from left to right, it's increasing. I know if you read backwards, it would actually be going down, but we don't do that. We only read from left to right. Now, if we were in China, it'd be a lot more complicated to describe that. But we read from left to right, so here we go. It's going up the whole time, so that's increasing in that whole little zone there. So how do I say what zone that is? Well, it increased from the very beginning, like from the very beginning of the graph. It started increasing right away. So it's increasing from negative infinity until I hit, where does it stop increasing? Right there. It stopped increasing. And then it's going to start to what? Decrease. So how do I say in this zone here, it was increasing from negative infinity until, the question is, should I use the negative 3.6 or should I use the 0.7? Yep. Because up until here, which is where 3.6 is, see, 1, 2, 3.6, that's where it was increasing in this zone here. How about this? In this zone here, maybe if I make the whole thing dark, do you get, if I do it this way, maybe this will help some of you. In that zone there, do you get it was increasing? So how do I say that zone? I say that zone from this way to that way. See? So I say that from negative infinity until negative 3.6, which is where it hits right here. In that zone, it was increasing. Okay, so I'm going to say like this. And did it actually, we just put parentheses around this kind. We don't think a lot about, is it at that spot or not at that spot? You don't have to use brackets. You just use parentheses for everything on this kind. Okay, decreasing. I think you all get that. At that moment, it starts to go down. It's like the roller coaster, and it keeps decreasing until there. But the way we say that is in this zone here, from here to here, in this zone here is where it was decreasing. So what is that zone? From what to what? Nope. Nope. It's where it left off. Negative 3.6. To where does it stop? We got to look at this one, and what's important, the x's or the y's? The x. Notice we use the x. Okay, we never have used the y's at all. So it's just the x's to negative 0.9. If the way you would use the y is if you ever wanted to know what's the lowest it went, then we'd say the y. Okay, so it's increasing and decreasing in those intervals. But do you get now it's starting to increase again? In this little zone from here until here, which I'm going to just extend out, in that little blue zone, it's increasing again. So that's from here to here. So in the blue zone, it's increasing, and that's between negative 0.9, and that's increasing. At where does it stop increasing? Right there, which is x-wise at the 1. And then it starts decreasing again, which is right here, and it goes down, 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 down. And therefore, in this zone, it is decreasing. All right, let's see if you really caught that. Here's a graph. Increasing from where to where? I have found that, yeah, try to answer it. Notice these are x's. Decreasing from where to where? Remember, your answers are x's. I think I figured out that warmth equals want to nap. And so if I turn this heater on somebody, it's like they slowly melt into their chair and start to become tired. And now, when you're really cold, it feels really good, but I'm going to turn the thing off because I don't want people sleeping right now. If anybody gets really cold, I know sometimes, by this time of day, my class isn't that cold, but in the morning especially, people can be cold. I let people ask if they want to have it pointed at them. Yes? Good question. When you're increasing, at the very top here, do you get how we could argue about whether you're still increasing when you hit the top? But the argument is, at that spot, at that exact spot, it's actually not increasing anymore. It stopped increasing right there. So that's why we use parentheses. All right, did you say from negative infinity until it hit negative 2.1, it was increasing? Raise your hand if you had that right. Okay, good. And decreasing from that moment on, which was at negative 2.1, until it hit right there, which was x equals 1. Raise your hand if you had that part right. Good. And did you notice there was a third place? In here, it was increasing again. So you needed another increasing one from 1 to infinity. Who caught that one? Excellent. That's increasing and decreasing, and that's really easy. All right. This one, let's just do one last one. Just tell me this one. In that zone right there, write down if it was increasing and decreasing, and if it's in the increasing blank or the decreasing blank, you only use x's to say the answer. Increasing from here to here or decreasing from there to there. How do I say that red zone there? Okay, so first in that spot, Miss T, what do you think it's doing? Increasing or decreasing? Wait, is it increasing or decreasing? It's increasing, so I'll put my parentheses here. And you think it's increasing from where to where? -5 to negative, I would agree that's some kind of decimal. Oh, it's -2.9. It says it right there. Cool. -2.9. I thought I'd have to read it, but it says that right on the board. And so, do you notice I only used x's? All right, good. Raise your hand if you had that one right. All right, good. So the harder part was, to summarize it, we had this. And we said, okay, I know that one ends going up or down. Be careful now. Is this an end going up or down? How does the story end? All right. Do you get how this is the biggest one and therefore that doesn't matter? That's why it's ending going up. And if on the right side it's going up, on the left side it must be down because it's opposite, because this is odd. Then one more thing. It has a y-intercept this time. The y-intercept is where x is 0, so that would be this. So it would have to go through the point -7. So could this possibly be the graph I'm looking for? Yep. And it's got a degree of 3, 5, or 7 because I can tell it's odd. Now, at most, it could have 4 turns. Did you notice I didn't say it has 4 turns? I said it could have as many as 4 turns. It can't have more. So it could be 4 turns. 1, 2, I'm going to go through that now. 3 turns, and then 4 turns. There, that might be it. That's the kind of thing you have to do on your test. You say, okay, give me a possible graph. That green one is possibly right. Because I know it ends going on the left, ends on the right. It ends with a happy ending. It has going down on the left, and it's hitting the right y-intercept. And it's got 1, 2, 3, 4 turns, which is 1 less than that. Cool. You learned everything that you needed to know. Now, we have to, unfortunately, because we had an easy day yesterday, I have to show you a couple things new on the new slide. You do not have to turn to this set of notes. I will just show you on the board here. This is that thing I was showing you before. Remember me saying that that's worth 2 because it's like a parabola? We call that a bounce. Double root. It's a bounce. We call this kind where it hits the x-axis a snake. It's a triple root. Okay, so that's a snake. That's a bounce. And this one is just called a single root. Where it touches is right here. I kind of don't like that it's got a red dot in that spot because that's not the important spot. The important spot here is where it hits the x-axis. And that's cutting through. It's not doing anything special. It's not bouncing. It's not doing that cool little curvy snake thing. So that's a single root. And if you think about it, this equation right here has just a 1 right there. Okay, this one's got a squared in it and it's got the bounce. This equation has y equals x to the 3rd and it's got the cool snake to it. So what does that mean? That means if I have this graph, you now know so much that you could tell me, okay, Mr. Server, I know it hits right here as a bounce, therefore that's giving me a certain number of degrees. This one's a normal cut through, and so that gives a certain number of degrees. And therefore, what degree do you think this one is? Say it if you know it. I think I know the degree. Do you? Degree 3. Does the fact that it has 2 turns match up with the fact it's degree 3? Yep. So I bet it's y equals x to the 3rd, except not. Come on, you can do this. It's got to have a negative because it ends going down, so it has a negative there. Okay, and then there's one more thing. This could be factored out into something like this. It's got a negative in front, and then it hits at 2 different spots. One of them is a bounce at -2, so it could be like this. And one of them is a cut through at like 7, and that could be like this. Do you get how this is like 7 and this is like -2, and those are like the roots that go in here and here? And do you get at this one, it's bouncing, so it's squared? Okay, so one more time. Here's another picture, and this is like the hardest state-of-the-art kind. That's a triple. That's a double. That's just a cut through. Let's say that this is at 0, this is at 5, and this is at 10. Then tell me which parts of this equation you understand. Do you get why I'm doing 3 sets of parentheses? Because there's 3 roots, right? I get that one of my roots is at 0, and therefore x plus 0 would work. And do you get one of my roots is at 5, and therefore x minus 5 would work for that? And last root is at 10, so x minus 10 would work for that. How about this? Who can see something else has to be different on my equation to match the graph? Yes, sir? Okay, and tell me the exponent that should be on the 0. You got it. Tell me the exponent should be on the 5. You got it, because it's a bounce, because that times is a bounce. And the exponent that should be on the 10, a 1. All right. Now, what degree was this? And yes, you're right. Just wait for last. What degree is this? Nope, not degree 3. And this kind, you have to add them all up. You have to act like you multiplied it all out. Degree 6. And does degree 6 match up with both of our ends being the same way? Yes. And the only thing that's missing is what you said.
Negative.
It needs a negative, so I can slap a negative on the front. How come you know there's a negative?
Because it has 2 going down.
Not because 2 of them are going down.
Because the right one's going down.
Because the right one is going down, exactly. There we go. That is as hard a problem as you'd have to do. Now, we have tomorrow to completely review everything I just taught you, so don't freak out. And we're going to have a little quiz on it after that. It's not going to be worth many points, but you'll have a little quiz on it in a couple days. You still have time. You'll have an assignment to practice over the weekend. I'll review everything with you on Monday, and then the little quiz. All right. So let's actually get to the homework. Your homework on this thing is, let's find day 2. So we're going to skip over day 1. I'm going to pause for a second, and I'll show you where it is. People there. All right. So we're in semester 1. So we're going in this folder. And then now we're in this thing called higher degree polynomials. It's unit 6. And then we kind of skipped through lesson 1. I reviewed all of it today. And then lesson 2 is the one I want you to do for today. And lesson 2's worksheet, it says lesson 1 and 2 worksheet. That's this. It's all one big worksheet for the last 2 days. Okay? So it kind of works nice. So you just have this one worksheet. Okay? And this worksheet, we are going to skip some of the problems on it. Okay? And because this worksheet has a lot of labels with A, B's, C's, D's, etc., it's going to be especially important to understand how to do, what we're going to do is even problems or even letters. Okay? All right, so I'll help you understand that. All right? Do you get to skip all of number 1? No. No. Even problems or even letters. Okay? So this is an even letter. You're going to do B and you're going to do D. Let's just do them really quick right now. You know what degree that is? That's all I got to answer. What degree is it?
4.
Degree 4. This is not the kind you add. That would be if they were all factored out. Okay? How about on D? What degree is that?
Degree 10.
Degree 10. Done. Okay? Let's move on. Even numbers and even letters. Okay? So on problem 2, all we have to do is the even letters. So the first one would be the odd one. So we're doing even. So we're doing B and D again. If you want to think of it as the BD problems, it's all the B's and D's from every single part. Okay? Even problems, even letters. Okay, so let's do B. This one is x to the 3rd. Ooh, I know that one. Kind of looks like this. And it says description of end behavior. Well, on the left, it's what?
Down.
Down. You can use D and U. It's fine with me to abbreviate. And on the right, it's what?
U.
Yep. Oh. I'm going to throw on an extra letter just because I'm that way. Okay, so that was B, and then we also do D. Oh, there's no D. Yay, I get to skip that one. Keep going. Number 3. Is that an even problem or an even letter? Nope, so we get to skip it. Number 4. Even problems and even letters. So this is, we're going to do B on this one. So negative x to the 8th. What am I supposed to do with it? I guess I got to read the directions. Bah. All right, describe the end behavior. Okay, I can do that. Left and right. It's negative in the front. Does that give you a hint? I always start with the right side because the negative or positiveness tells me the answer. The right answer is down. Do you know why I picked that? Because it was negative in front, and that's a sad ending. Ends going down. On the left end, I always look at the degree, and I say to myself, should it be the same or different? If it's degree 8, it's an even, and so that sounds to me like the same. If it had been odd, that sounds different to me. But anyway, even, same, so therefore down. All right. And D, here we have a negative in front. So my left side, my right side, I'd start with the right side, down. But since it's degree 9, that's odd. What should the left be? Up. Because they're different, because it's odd. Oh, wait. And then the rest of the directions say, and whether the leading coefficient is positive or negative. Oh, that's just telling me how to do it. Okay. Just wanted the left and the right end behavior. So we're doing it right. Okay. Keep on going, and let me clear my stuff. It's problem 5. Do I just get to skip the whole thing? No. You do the even problems and even letters. So the even letters here are the B's, D's. So let's do this one. The end behavior of an even degreed function with a negative coefficient. It's just like telling you the equation in words. This one start with a negative. Yep. So what's the left side? What's the right side? Always start with the right side. What's the right side going to do? Down. Why is it down? Because it leads with a negative coefficient. And the left side? Is it the same or different? It's the same because it says even. So if it's the same as down, it must be down. Make sense to you? All right. Let's get to some of the harder ones. As I move on to, let's get all the way near the end here. Even degrees and even letters. We're in this neighborhood, let's say in here. Okay? And the directions say, write the equations of the following graphs in factored form. Remember, that just means like 2 parentheses. We're supposed to do the B's and D's, right? So we're doing that one. Here's parentheses. Remember me showing you this a second ago? There's only one root, so I only need 1 parenthesis, right? And it looks like it's touching right there at negative what? Negative 1. And so this is x, is it minus 1 or plus 1? Plus 1. And is it squared or cubed or to the first? Squared because it's a bounce. Done. That's it. Oh, wait a minute. I almost forgot something. You caught it, didn't you? It's going down on the right, isn't it? Since it's going down on the right, needs a negative. You could put it inside, but then the squaring would get the negative off of it. Negative on the outside. It's so easy to forget that negative. Everybody forgets the negatives. Good question. We aren't going to worry about stretching on this one because if I go over 1 and down 1, it ended up hitting there, so there's no stretch. It's a good point, though. I'm glad you noticed to think of that. All right, pausing for a second. All right, so let's go to some other even letter. Look at section 6 here. Looks like that might be it. So this is an even problem, and if it doesn't have any letters, I have to do the whole thing. So I guess I should just do number 8. Oh, the extreme values. I'm glad we went to this because I hadn't talked about these. These are super easy. It's just high spots and low spots. Do you get that that is a high spot? What's the name in math for a high spot? Good. What's this called then? Minimum. All right, that's all there is to it. And do you get how they're extreme? Because in their neighborhood, like this person would live on the top of the hill in their neighborhood. They are the highest point. They are the local maximum. Locally, they're the maximum. And locally, this is the minimum. Then the only thing that adds complication is this the highest spot of them all? Because if it is, it's the absolute maximum.
No, that's not the highest.
No, because this keeps going up, doesn't it?
Yeah.
So this one, this graph has no maximum. It has a local maximum. Locally, there's somebody who lives on the top of the hill there, but there is no absolute maximum. That's the difference. These are extreme spots, but there is no max and there's no min. Because if this side would extend that side, it would go down forever, and therefore there's no absolute minimum, no absolute maximum. But there is a local extreme spots, and they're the local max and the local min. So this spot right here, is that a local max? No, it's called a local min. This spot here, is that a local max or a local min?
Local min.
That's a local min. How about that spot?
Local max.
Local max. How about that spot? Local max. Notice there's no minimum and there's no maximum. Last example for you is if you were to take a graph that goes like this, That spot is the highest of them all. So not just the max, absolute max. Okay? It's locally the max and it's the absolute max. That's one thing a lot of people get confused is, what do you mean? You said that that was a local max. Do you get if there was a kid in here who was the strongest of all the kids in this room locally, he'd be the maximum? Okay, let's say it's Ted. All right? Now imagine for a moment that Ted was also the strongest kid in the entire world of his age. Is there some kid who is that? Yeah. That kid's locally the max and he's the absolute max. So if he's the strongest and the strongest in the whole world, he's locally and absolutely the max. You can be both. So this is a local max and it's an absolute max. All right, it was a long lesson for today. Thanks for hanging with me on that. Even problems and even letters. And that's all I got for the video for today.